Okay, so remember how kinetic energy and mechanical energy worked? Remember how kinetic energy was half of mv squared? And how potential energy was mass times gravity times height? And how mechanical energy was kinetic energy plus potential energy? Well, that's for linear, but now just think in the rotation sense. Okay, so remember how velocity, acceleration, and displacement are all linear? Okay, and then to convert from linear to rotational or angular, all you would do is just divide by the radius. So it would be W equals velocity over R, angular acceleration equals acceleration divided by R, and displacement divided by R is equal angular displacement. With W being angular velocity, the fishy thing being angular acceleration, and triangle theta being the angular displacement. And remember how the m and force equals mass times acceleration became inertia and torque equals inertia times angular acceleration? Well, the same thing applies to kinetic energy. Since linear kinetic energy is half of mv squared, that means that angular or rotational kinetic energy is equal to half of inertia angular velocity squared. It's pretty simple. Okay, so let's say the question asks you for the total. Notice how I emphasize total kinetic energy. That means that you find the linear and the angular values. So your final answer for the total of kinetic energy should be half of mv squared plus half of inertia angular velocity squared. And then when the question asks you to find the total mechanical energy, that means that it's kinetic energy plus potential energy, which means it's half of mv squared plus half of inertia angular velocity squared plus the potential energy, and then that means that the potential energy is just mgh, mass times gravity times height. Okay, so a thin sheet of plastic is uniform and has the shape of an equilateral triangle. Consider two axes for rotation. Both are perpendicular to the plane of the triangle. Axis A passing through the center of the triangle and axis B passing through one corner. If the angular speed about each axis is the same, for which axis did the triangle have a greater rotational kinetic energy? Okay, so let's begin by drawing this out. So we have two triangles there and the axis is of rotation. The kinetic energy is half inertia W squared, and the kinetic energy is half of inertia W squared for triangle 2. Let's separate them, the values, and now let's break inertia down into mr squared. Okay, so I apologize for that. I didn't realize that it was still recording. Okay, so let's read this. A hoop, a solid cylinder, a spherical shell, and a solid sphere are placed at rest at the top of an inclined plane. All the objects have the same radius. They are then released at the same time. What is the order in which they reach the bottom fastest first? Okay, so look at the equation sheet Burgos gave you and write down the inertia for each of those four objects. And we're getting that the hoop is mr squared, the cylinder is half mr squared, the shell is 2/3 mr squared, and the sphere is 2/5 mr squared. Okay, so any object that has less inertia will travel fastest. So you just have to list these in order from the ones that have the least amount of inertia, which are also the ones that get there the fastest. So the one with the least inertia is sphere, and then it's cylinder, then shell, and then hoop. And that's because of the coefficient in the equation of the half, of the 2/3, and of the 2/5. Okay, this problem looks like it's long, and it sort of is long, but it's really easy. Okay, so let's read. Three objects lie in the xy plane. Each rotates about the z-axis with an angular speed of 6 radians per second. The mass m of each of the objects and its perpendicular distance r from the z-axis are as follows. m1 is 6 kilograms and r1 is 2 meters. m2 is 4 kilograms, r2 is 1.5 meters. m3 is 3 kilograms and r3 is 3 meters. So find the tangential speed of each object. Okay. So first things first is write down your values. We know that the angular velocity is going to be 6 radians per second, and m1 is 6 kilograms and r1 is 2 meters. W2 is 6 radians per second, then 4 kilograms and 1.5 meters, and then for the other one it's 6 radians per second, 3 kilograms and 3 meters. The reason that we know it's 6 radians per second is because the problem says each rotates with an angular speed of 6 radians per second. Okay, so now let's solve A, which asks us to find the tangential speed. Okay, well we know that tangential speed or velocity, the equation is angular velocity multiplied by the radius. So let's just write down those values and substitute. So we get 6, okay, so we get 6 times 2, which gives you 12 meters per second. And I'll do the same thing for the blue one. We get V equals WR. So we get 6 times 1.5, and which equals 9. And then we do V equals WR for this one. And we do 6 times 3, and we get 18 meters per second. And that's all you have to do for part A. Okay, so this is what we have in total. Now B asks you to determine the total kinetic energy of the system using that long equation. Okay. So they're only asking you for linear kinetic energy because look at the equation. It's just half of mv squared. It doesn't deal with inertia or angular velocity. So let's write the equation down, color code it to make it easier to understand. And then you just substitute in your values. Once you substitute in your values for m1 to be 12, for v1 to be 12 and m1 to be 6, and then m2 to be 4, and v2 to be 9, and m3 to be 3, and v3 to be 18, once you plug in those values, you get 432 plus 162 plus 324. And then once you add that, you should get 918 joules. And that's the answer for B. Okay, now C asks you to obtain the moment of inertia of the system. So that means to find the moment of inertia of each individual object and add them up together. So we know that inertia is just m1 r1 squared plus m2 r2 squared plus m3 r3 squared. So you just plug in for those values and you should get those numbers, and then when you add, that should be your final answer, 60 kilograms times meter squared. Okay, now we do part D. And part D says to find the rotational kinetic energy of the system. So we can do this two ways. Here's the first way. You find the rotational kinetic energy for each individual object and then you find them. So that's what we're going to do. So half of inertia W squared plus half of inertia W squared plus half of inertia W squared, and then you plug in for the values and you get those, and then you add and you get 1080 joules. The other way you can solve it is, since you already know the total inertia for the system and you know that all three objects go at 6 radians per second, you just plug in half of 60 times 6 squared and you still get 1080 joules, because that half of 66 squared is the half of the net inertia, which is this one, times the W squared, which is 6. So see, that wasn't that bad at all. It was just a long question, but each individual answer was pretty easy. Okay, so two thin rods of length L are rotating with the same angular speed about axis that pass perpendicularly through one end. Rod A is massless but has a particle of mass 0.66 kilograms attached to its free end. Rod B has a mass of 0.66 kilograms, which is distributed uniformly along its length. The length of each rod is 0.75 meters and the angular speed is 4.2 radians per second. Find the kinetic energies of rod A with its attached particle and rod B. Okay, so first write down what you know. So for rod A, you know that the mass is going to be 0.66 kilograms. You know that the length is 0.75 meters, that the angular velocity is 4.2 radians per second, and that the inertia is going to be 1/3 ml squared, because the equation sheet says that for any rod that has an axis at the end, the inertia will be 1/3 ml squared. And now for rod B, you know that the M is 0.66, the L is 0.75, and the W is 4.2, just like rod A. But since the mass is distributed uniformly throughout, the equation sheet says that the inertia is half of ml squared. Okay, these are the values that you know. So first, let's plug in into 1/3 ml squared, which is 1/3 of 0.66 times 0.75 squared, which if you put that in your calculator, you'll get 0.123, you get 0.12375 kilograms times meter squared. And then for rod B, you plug in for 1/12 of ml squared, which would be 1/12 times 0.66 times 0.75 squared. And then you plug that into the calculator and you get 0.0309375 kilograms times meter squared. So those are the inertias for each rod. And now it wants you to find what was it that I wanted you to find? Let me check. Okay, I wanted you to find the kinetic energies. And kinetic energy is half of inertia W squared. So now you just plug in for half of inertia W squared plus half of inertia W squared. You plug in this number for the I and this number for this I, and you already know that the W is 4.2 because it told you. So you just plug in and you get that number for the rod A and you get this number for rod B, and you just add them together and you get 1.36 joules. And that's it. So now that's kinetic energy. Nice.